Alright, so welcome to this video series. The goal here is to look at machine learning methods as implemented in R. This video series will mainly focus on the more conceptual components of the machine learning process. So, for example, we're going to look at uses of machine learning in GIS and spatial analytics. We'll talk about the process of doing machine learning, how to prepare data, create training data, validation data. We'll talk through some of the common modeling techniques that are used or the different algorithms. Then we'll look at accuracy assessment and then some more specific topics related to, dealing with like imbalanced data, tuning hyperparameters, doing data pre-processing. The practical components will be introduced mainly through Caret, which is an R package that allows you to implement a wide variety of different machine learning algorithms using a common syntax, and also the more recent Tidy Models package, which is going to replace Caret. So this video series was funded by AmericaView and the USGS, and it's an update of a prior video series on the same topic where we're just trying to update the material and reflect some changes in the software and introduce some new concepts. Okay, so before we get into it, just a note, so we've tried to use kind of a standard color coding scheme through the slides here. So we use this tan color for basically plain text, headings are in yellow, keywords and key terms associated with machine learning and like geospatial science will be in orange. Terms that are R related, like packages and functions, are going to be italic and green. Captions are in blue, web links are in purple, and then some references and whatnot will be in red. Okay, so we're going to talk first about just some use cases of machine learning techniques in the geospatial sciences. Okay, so here's an example of a common use case for machine learning methods. So this is basically the concept of thematic mapping or general land cover mapping, where our goal is to extract categories or classes from remotely sensed data such as imagery and other ancillary data such as like LiDAR derivatives. So this is a classification problem where we give it input, imagery, and data, and the output is the landscape broken into a variety of classes. So for example, the random forest and the support vector machine algorithms have kind of become the standard for image classification using machine learning. Here's just another example. The goal here is to try to differentiate grasslands from other land cover, and then differentiate grasslands that resulted from surface mining from other types of grasslands on the landscape using a series of different machine learning steps and processes. So anyway, that's just another thematic mapping example. Sometimes we're interested in something that's not like a hard classification where we're trying to break the landscape into a set of categories. Instead, we're interested in kind of a soft or probabilistic classification. So in this case, instead of getting back categories, we get back the probability or likelihood that a location or cell or pixel or aggregating unit is going to be in one of a set of categories. And this specific example relates to wetland mapping, so trying to predict the topographic likelihood of wetland occurrence. We can also try to make predictions into the future. So, for example, this is from a paper in which the authors tried to estimate the likelihood that certain locations may be surface mined in the future, and this was done for the entirety of the Mid-Atlantic region here in the eastern U.S. So the red areas were suggested at a higher likelihood, and the blue areas were suggested as having a lower likelihood. Okay, so anyway, that's just a few examples. So there's lots of options, lots of use cases for machine learning for those of us who work with geospatial data. Thematic mapping is mentioned here, modeling, in ecology, there's options like, or uses such as, habitat modeling, and whatnot. So lots of uses, so that's why we're interested in exploring machine learning as a topic within our discipline. So now we're going to look at what the kind of broad types of classifications or predictions we can make. So our first group here is going to be numeric or continuous outcomes. So here we're trying to predict a continuous variable, so a ratio interval type data. So generally we would think about doing this type of process using like linear regression or multiple linear regressions or some other type of regression technique like polynomial regression. But this is also something that we can use machine learning for and other more complex methods like generalized additive models and even deep learning. So this is an example of a prediction of a numeric or continuous variable. So this is a product from the 2011 National Land Cover Database. So they don't just generate thematic maps with this, they also make some other predictions. And here they're predicting percent canopy cover. So the outcome that's being predicted is a continuous variable or percent of a pixel that's covered by forest canopy. Okay, so that's a regression type problem. So we'll look at some examples of those later and also the type of assessment metrics we would use for the regression techniques. Instead of trying to predict something continuous, you may be interested in predicting a category or a nominal variable. So examples include things like land cover types, soil types, maybe like land use types, types of wetlands, types of, say, forest communities or ecological zones or whatnot. So the goal here is effectively unordered categories or nominal data. There's lots of techniques that have been applied to these types of problems in the past. So, for example, logistic regression for like binary classification problems, and then our standard non-parametric techniques that you may have learned about if you took a remote sensing class, like maximum likelihood, parallel pipette, minimum distance to means. But obviously, machine learning, deep learning, and whatnot is also applicable to these types of problems. Binary classifications are just a kind of a special case of categorical predictions where you just have two categories. So this could be like suitable or not suitable, in this example, grassland or not grassland, or like yes, no, whatnot, right? So, but that obviously can be expanded into multiple categories. So having more than two classes to differentiate. Just as a quick side note, what we're going to be looking at here specifically is supervised learning. So with supervised learning, you're effectively giving the algorithm examples, so as training data, and then you're using an algorithm that then takes those examples, learns from them, and tries to produce a model. So it's supervised because it's getting examples up front that it's using to try to make the predictions. This is in contrast to unsupervised learning, where effectively the algorithm or method doesn't take trained data up front. Instead, it uses the methods rely on some type of clustering, where it tries to group pixels or aggregating units into similar types, and then afterwards the user is going to have to take those types and assign them to actual useful categories. So in remote sensing, we talk about taking like pixels and converting those into like spectral clusters, and then manually recoding those into like informational groups, such as like land cover types. So the key thing here is we're going to be looking at supervised classification, which means we need to provide it training data up front. So those should be individual pixels or data points or aggregating units that are labeled with whatever we're wanting to predict, and then also the predictor variables such as image bands or elevation derivatives or whatever we're using as our predictive space. There's a whole separate group of algorithms and techniques associated with unsupervised learning. That's still a really active area of research, but we're not going to discuss that in this specific context. If you're interested in reading just on kind of the applied use of machine learning in remote sensing and image classification specifically, here's a link to a paper, and this paper is an open access. So if you go to the link there, you'll be able to read it without getting a paywall or having to purchase it. But a lot of the material that you'll see here came from this study a review article that we put together several years ago, so we were drawing from that experience. Okay, another option or type of prediction is trying to predict a probabilistic outcome. So instead of a hard classification or taking the landscape and breaking it into different categories, we get back the likelihood of being in a class or the likelihood of being in a set of classes as a probability. So really this is just classification, it's just that the output's different. So instead of a hard guess, you're getting back a class probability. And that could be binary for yes or no or two classes, so for example wetland or not wetland, but it also could be multiple classes. So again, that's really just a special case of a classification problem. So we basically use the same types of methods. So logistic regression, generalized additive models, and then obviously machine learning and deep learning. Okay, so now that we kind of have a broad overview of what it is that we're trying to accomplish and some of the use cases and the geospatial sciences, remote sensing and GIS, we're going to talk through the process that we actually use to actually implement these types of processes or techniques, make these types of predictions. So again, basically machine learning is simply learning from examples, especially when we're talking specifically about supervised learning. So these are all empirical modeling techniques, so learning from examples. So the idea is that we basically are trying to predict something. So we have to give the algorithm examples of things that we want to predict. And then we also need to give it variables or information that we do have that we think might help make that predictions or that are predictive of the thing that we want to map or predict or model. So things that you think might help you predict the new thing. So anyway, we basically take those input locations or data points, those independent or predictor variables. Those get fed into some type of machine learning method, and we'll talk about some different options later on in the series. The model is then trained, and then you have a model that can be applied to new data. So to make new predictions, we basically feed new data into that model, make the predictions, and get an output. When we're working with map data, a lot of times our output is going to not just be like a table, but actually a contiguous map output. So like predicting points to points or polygons or every pixel in an image stack or something. So in this specific example, these actually represent locations where there have been landslides. So the red dots there are initiation locations such as headscarps for landslides, and then the black points represent areas where there weren't landslides. So this is basically a binary classification problem, so we can get back landslide or not landslide, or the probability of being a landslide or not being a landslide. And then we have a set of predictor variables here. Most of these are things related to lithology, like in geology and soil and terrain characteristics, like such as slope and surface roughness. So that's our input space. Then we train that model. We throw back in new data, and that new data in this case is going to be pixels, because we're going to try to make a prediction at every location on the landscape. And then we get back an actual raster-based map output. So in this area, the red zones were predicted as having a higher likelihood of slope failure than the yellow and green zones. And this is a probabilistic type output, so higher probability of being in the slope failure class. Okay, so here's just kind of a broad overview of the general process, and obviously with every problem is unique, so you may diverge a little bit from this kind of standard workflow, but these are the common things that we have to do. Okay, so the first thing we need to do is develop some training data. Again, this is all supervised learning, so you have to give it examples. You're learning from examples, it's empirical. Also, you need to develop predictor variables. So these are the independent variables or the predictor variables or the feature space, or basically the things that you're giving the computer that you think will help it predict whatever it is that you want to predict. So that could be image bands, elevation, topographic slope, whatever. So variables. You also need to develop validation or testing data so you can actually assess the model. And we'll talk about the characteristics that those type of data should have to actually get a nice, unbiased, realistic assessment of your model performance. Then you need to prepare your data. Generally, we call that feature space engineering. So this could be like GIS pre-processing, like clipping and merging and stacking data, rescaling data, normalizing data, whatever. So we'll talk about some of those techniques throughout the series. Then you generally want to optimize the algorithm. So we'll talk about how we do that. Basically, hyperparameters are settings or values that aren't learned but that the user must provide. And for certain tasks, those settings can have an impact on the output. So there are techniques to try to find the best settings. Then we train the model with our training data. So now we're down to step 6 here. And then once we have a trained model, we can use it to predict new data, such as the validation data. Once we predict the validation data, we can use we can estimate or assess the model using a variety of assessment metrics, and we'll look at examples of those later on in the series. And then if you're satisfied with your model, then you can use it to predict to an entire spatial extent, such as every pixel across your landscape or every polygon or whatever your unit are, and obviously save those results and whatnot and report. Okay, so let's talk about training data. So training data should have these general characteristics when we're specifically talking about doing spatial modeling. So they should be spatially explicit. Basically, we need to know where they occur on the landscape. So here I have a bunch of polygons that are examples of different land cover categories. Here are top of Vancouver in British Columbia. So these are spatially explicit. They map to a certain location on the ground. They should be representative of the population. So for example, if you were trying to differentiate forest communities, and a specific forest community, grows, say, in coves, but also maybe like in valley bottoms. So if you only gave it examples in the coves and no examples in the valley bottoms, then that's not truly representing the population, right? So you need to give it a nice representation of the population in order to accurately predict back to the population in an unbiased way. And generally what we mean by population in this context is all of the units that you're predicting to. So for example, image pixels or polygons or whatever. You generally have to have an adequate number of samples and also an adequate number of samples per category. So if you're doing classification in each of your different map categories. So the question here obviously then becomes, what is an adequate number of samples? Well, this is kind of a lame answer, but honestly, that just kind of depends on the problem. So if you have like classes that are really difficult to differentiate, or there's a lot of variability, or maybe it's a large spatial extent, you're probably going to need more samples than if you're trying to differentiate something that's simpler. So for example, in this image, if our goal was really just to differentiate water from everything else, that would probably require less training data than if you're trying to differentiate all these multiple classes. Generally, my rule of thumb is I try to get as many training samples as I can given the limitations, right? So time, money, data, whatever, right? So I know that's kind of vague, but there isn't really a good solid answer for that. There's no even rule of thumb really. It's just problem specific. You can always train a model, and if it doesn't do well and you think you didn't give enough data, you could always create more data and try to improve the results potentially. Other than just having an adequate number of samples, it's also important to have an adequate number of samples per category. So if you have 5 categories and you have a total of like 1,000 samples, if one of those categories only has, say, 10 or 15 samples, that's probably not going to be enough for that specific class, and you may have difficulty mapping that class while the other ones are mapped well or differentiated well. That's kind of the concept of having an imbalanced data set, which we will talk about throughout the series here. And obviously these data need to be accurate, right? So if you feed it in bad data, you're probably going to get a bad result, right? So garbage in, garbage out, right? So accurate basically means that for classification, they should be assigned to the correct category. They shouldn't be mislabeled. For regression, the numeric measure you're trying to predict should be correct. So it's not always easy to get quality data, and obviously, and even harder to get a large set of quality data. But in many ways, that's sometimes the most important factor. In fact, in a lot of the current literature on deep learning, there's a lot of research on developing new algorithms and new training methods and optimization algorithms and whatnot. But a lot of people are showing that the most important factor generally is the number, abundance, and quality and characteristics of the training data. Okay, just as kind of a side note, sometimes we're in a situation where we have examples of the thing we're trying to predict, but we don't have examples of not the thing we're trying to predict, right? So, for example, if you're interested in mapping an animal habitat, you might have points that are that animal habitat, but none that aren't. Or if you're mapping wetlands, you could have wetland locations, but not upland or not wetland locations. So in that type of situation, we generally need to develop what's known as pseudo-absence data. So effectively, these are going to be random points that are highly unlikely to actually be in the present case, right? So for example, if you had a landscape, let's go back to the slope failure mapping example. So if you had a landscape where you mapped all the slope initiation points and you didn't miss any of them, so that was basically a wall-to-wall mapping, then you could just pick random points, and since you mapped all the slope failures, the random points are unlikely to actually be slope failures. And then also you could do some cleaning up, such as if they're within a certain distance of a slope failure point or something, you could remove them, right? So that's sometimes easy, sometimes it's difficult. But this is a common problem because most of the learning algorithms that are available need examples both of yes or no or presence and absence. You can't just give it presence data. So in situations where the absence data doesn't exist, there has to be a way to feed it in background or pseudo-absence type points. And if you're in that type of situation, generally the best thing to do is to look at what type of techniques or methods people are using in your field or discipline to deal with that problem. How are they collecting background or pseudo-absence points? What type of assumptions are made? Okay, so I just wanted to note that because that is a really common problem that we run into. Okay, then we obviously need our predictor variables, our independent variables, or the features that we're going to use to predict a thing that we want to map or predict or whatever. Okay, so similar to the training data, these features should be spatially explicit. So you need to know values at specific locations. They should be accurately georeferenced, so you don't introduce errors from errors associated with positional inaccuracies into your model. Should be accurate and precise. They should be timely. For some characteristics that might matter more than others. So for example, bedrock geology is not going to change quickly, at least not over human timescales. That's more of a geologic timescale feature. However, things such as population or development or amount of impervious surface might actually change pretty quickly. So a data set that's 10 years old may actually be out of date in one situation, but in another situation it's fine. So that really just depends on the variable and how rapidly it's changing and conditions in the specific landscape you're mapping. They should be of adequate spatial resolution. So if you're trying to predict fairly small or detailed features on the landscape, you may need to have higher spatial resolution data than if you're trying to map, say, like a general pattern or something. And this last point here is kind of self-explanatory, but it's important. These data have to be available, right? So I've been in a lot of situations before where I'm going to undertake a modeling process, and you think, okay, so I need this information. I'm sure that exists. But then when you go to look, you actually don't find anything, or the data that you do find is not complete, or it's not of high quality. So sometimes we can't give the algorithm all the information we want because there isn't good data for that. And then again, when you get data that's noisy or incomplete or might be inaccurate, the question becomes, is it worth including it or not? One common example that I run into is variables associated with soil. So things like depth to bedrock, percent clay content, depth to water table. A lot of this, at least in the U.S., would come from like the Surgo data that was conducted years ago, generally, and on a county-by-county basis, so it's not generally consistent over large spatial extents. So I just honestly try to avoid those features. An example of inadequate spatial resolution is a lot of our data associated with climate, so things like precipitation, like mean annual temperature, seasonality related variables. Those tend to exist at a coarser spatial resolution, maybe like a 500 meter pixel. So if you're trying to do modeling at like a 30 meter resolution or lower, that's not really going to be adequate. So that's actually a large part of this process, is finding good input data and preparing it for an analysis. Another key point is that the data need to basically be, if you want to make a prediction everywhere, then you need to have variables that exist everywhere. So for example, if you're using like satellite imagery, you want to potentially predict back to every single pixel over an extent, issues like cloud cover could be problematic, because at specific cells you actually don't have spectral values associated with the land surface. You have spectral values associated with clouds or cloud shadow. Here's just a few examples of some predictor variables related to topography. And these are all derived from a DEM or DTM, digital elevation model, digital terrain model. So this is slope position. It's basically a measure of ridge versus valley. So high topographic positions to low. This is topographic dissection. It's a measure of incision. And this is topographic roughness, so local variability. So these are examples of generally decent spatial resolution, spatially contiguous, fairly accurate. Okay, so just some notes about doing this type of work inside of R specifically. So in R, if you're going to deal with raster data, and again, that's common that we want to predict onto or back to raster grids or stacks of raster grids. This is generally accomplished using the raster package. That's the kind of go-to package for working with, analyzing, processing raster-based geospatial data in R. If you have single band raster data, that can be read into R using the raster function from the raster package. If you need to read in multiple band rasters, like a multispectral image, that's generally done with stack or brick. The difference is that stack can reference multiple layers, so they don't as a single object in R. So you could have like a couple sets of images that all get read in and treated as one unit or one stack, whereas brick is meant to reference just one multi-band data set, such as one image. These are the different classes related to that. So raster layers are reduced by raster. Again, those are single band. And then raster brick and raster stack, those are multi-band. Raster brick just references one file, such as one multispectral image. Raster stack can reference multiple images or data sets and kind of treat it as a single unit. So generally, if you're worried about efficiency, if you're referencing just one layer, it's better to use brick as opposed to stack, and only use the raster stack if you're referencing multiple data layers. Another note is that I've generally found that R is a lot less forgiving than say like ArcGIS Pro, when you're dealing with layers that have different cell sizes, different numbers of rows and columns, different spatial extents or projections or spatial reference systems. So it's generally best if everything lines up perfectly. And for that reason, I tend to do a lot of my data pre-processing and stacking not outside of R, like in QGIS or ArcGIS, as opposed to doing it in R. Okay, so it should be noted that recently the raster package is being superseded or being replaced by the Terra package. Terra was produced by the same originators as the raster package, and it is intended to be a replacement. Raster is a really great tool, but it can be a bit slow. It requires reading a lot of data into memory, so it's can be difficult or impossible to work with really large grids unless you process things using like small tiles or something. So Terra basically tries to modernize this a bit. So for example, it's written using C++. It's really fast. It doesn't have to read the entire raster grid into memory all at once. So in the future, this is more than likely going to be the way we deal with raster data in R. And it is a bit different than the raster package. So again, it's generally faster and more memory efficient than raster. That's basically why it was created. Again, in contrast to raster, you don't have to read the entire raster data set into memory or RAM. It can work with it kind of in pieces. It actually uses a whole new class, which is the SPAD raster class. There's also SPAD vector and SPAC vector and then SPAC extent classes for dealing with vector data and then coordinate extents and whatnot. We're not mentioning that here, just mainly talking about the raster stuff. So again, it's written in C++, so it's pretty fast. It uses RCPP for the R and C++ interaction. Instead of using raster, stack, or brick, all raster layers are read in using the rast function, and that is regardless of the number of bands. So multi-band, single band, doesn't matter. It's read in with rast as opposed to the other options that were available for raster. And then there are functions available for applying models to raster grids to make predictions. So in short, if you're just starting to get into this, I would highly recommend trying to pick up and use Terra. There's not as big of a user group yet, and there's not as many examples, but it is more than likely going to be faster and more efficient than using the older raster package. If you've been using R for a while and you're used to raster, it works for you, that's fine. If you are dealing with issues of memory and whatnot, you're probably going to eventually need to update to Terra. So in short, I highly recommend checking out Terra if you haven't already or you're new to this environment. Okay, just a couple notes on common pre-processing tasks. So for when we're dealing with raster data, one common need is to merge or mosaic data sets together. So for example, if you have a bunch of little tiles that represent, say, pieces of an elevation surface, you might want to merge all those together using to one single image, so you don't have to work with each individual file separately. So for example, in ArcGIS, that's generally accomplished using the mosaic to new raster tool. Another kind of going the opposite direction, sometimes you want to extract out a portion of a larger data set. So here I'm extracting out only this DEM, or a portion of this DEM that's within this watershed extent. So that can be done with the clip raster tool or the extract by mass tool. So merging extents together or pulling out a subset from a data set. One thing I will note is generally it's best not to just work up to the edge of wherever you're wanting to map. So if you have a study area extent, generally it's best to buffer it out a bit and work out to the edge of the buffer as opposed to the edge of the actual extent, just so you have some wiggle room. So for example, with raster data, if you do some moving window type analysis, sometimes since there's not a full set of neighbors, it won't work around the edges, so you actually end up with a smaller extent or a less number of rows and columns after the fact. So if you have a buffer around the data, that generally will help alleviate that issue. Another thing you may want to do is stack data into a single multi-band or multi-layer image, right? We generally think about doing this with imagery data, right? So you have a bunch of spectral bands like red, green, blue, near infrared, and we stack those up into a multi-band image for display or analysis. However, it is possible not just to stack imagery, but any type of raster data. So for example, you can make a stack of climate variables or digital terrain derivatives like the ones I showed on the slide earlier, or even a mix of things like spectral bands, enhancements, band ratios, digital terrain variables. One note is when you do this, generally because it's a single file, all the bands will have to get converted to a common data type. So if you have a bunch of 8-bit data and then you want to merge that or stack it with one layer that's, say, 16-bit, then generally you're going to have to convert everything to 16-bit. Generally the tool actually does that itself, but you should know that that'll happen, which means it's going to make the files probably larger. So if, for example, you have a bunch of 8-bit data and one of the layers is float that you want to add in, then everything will get converted to float, which again can make the data set a lot bigger. Again, R is not always that forgiving with issues of projections and cell size and numbers of rows and columns and differing origins or spatial extents. So I like to do this type of stacking, even though you can do it in R. I prefer to do it in my GIS, QGIS or like ArcGIS Pro. Okay, so now we'll talk about validation data. So validation data generally need to be unbiased, and generally the way we accomplish that is by making the data randomized. So if you handpick locations to assess your model against, that's unlikely to be representative of the actual population or all the cells or aggregating units that you're wanting to map, right? So for example, if you are creating field data and basically you're just driving along a road, getting out occasionally and collecting points along the road, those points along the road are probably not going to be representative of all the points in the landscape, right? So, so in short, to actually get a nice unbiased estimate of your model performance, you really need to have unbiased data that are collected randomly. So for example, in this image, in order to validate the model, I basically just created a bunch of random points across the extent, and then I had to go to each of those points and photo interpret what type of land cover it was. So they weren't hand selected or convenient. It wasn't a convenience type sample, it was a random sample. Generally, it's best that your training data and your validation or testing data are non-overlapping. And the reason for that is that machine learning models tend to overfit, which means that they'll do a better job at predicting back to the data they were trained on than new data, right? So if you have some samples that occur in both your training and validation data, that can optimistically bias your assessment. So your training and validation data should be separate partitions and non-overlapping. This point, correctly proportioned, this is something that honestly most people don't do because it's not always easy to do, or people aren't aware that this should be done. But if you're actually trying to assess a map, it's generally best if the validation samples are proportioned roughly the same as they would be on the landscape. So if you're doing a categorical prediction, if say 10% of the landscape is forest, then that means roughly 10% of your validation data should be forest, as opposed to say 50%. It's actually much more common for people to do like a stratified sample where you have say 100 examples or 1,000 examples of each class. But that assumes that on the landscape there's a equal proportion of all types, which isn't necessarily the case, and actually more than likely it's not the case. So to actually approximate or assess the accuracy of the map, we want to have these data points correctly proportioned. And again, that's not always easy to do, and this is especially difficult when you have classes that are rare. So for example, in this image, one of our categories was barren lands, so things like rock outcrops and whatnot, bare like agricultural fields, and that's not very common in this landscape, so we get a fairly small number of those features in our training set for that reason. And obviously they need to be accurate. In remote sensing and geospatial science in general, we try to avoid using the term ground truth because that implies that the data are like 100% correct, when in truth no data are 100% correct. So instead we tend to use the terms reference data or validation data, testing data, as opposed to, again, ground truth. So we try to collect the best data that we can. The assumption is that it's quality and probably more accurate than the model that you're assessing it against, but nothing is going to be perfect. Here's just a couple notes on creating training and validation data. So again, I prefer to do this work outside of R in GIS software like QGIS or ArcGIS. There are different methods to like collect values or summarize on different aggregating units or points or whatever. And generally what we end up with is a table that's going to have the thing we're wanting to predict, so our dependent variable, and then all of our predictor variables that were extracted from our feature space or our like raster grids, so image bands, elevation derivatives, whatever. So that's generally going to be like a CSV file that comes out of separated values or some type of table. Okay, so let's just briefly, I wanted to mention some tools for doing this type of data preparation inside GIS, and here we're going to look at some tools in ArcGIS Pro, and they're comparable tools in ArcDesktop like ArcMap. So for example, if you need to extract raster values at point locations, so like image band values, elevation, land cover, whatever your raster grids are, that can be accomplished with either the extract multi-values to points tool or the extract values to points tool. Even if I'm only extracting values from one raster, I prefer to use the extract multi-values to points tool because it allows you to like rename the attribute columns that you're going to get. And effectively what this is going to do is it's just going to add the cell values at the point locations into the table for the point features that you're using. So here we can see at each of these points we've grabbed the elevation measurement from an elevation grid, and then the land cover from the land cover grid. And here this is the code as opposed to the like character string. Note that this generally, the way it works in Arc Pro is this writes into the original data table. So if you're worried about screwing up the data table, then you can always do this on a copy. And then if you don't need the spatial information, you can always export out just the attribute table to bring into R. Okay, some other methods for data summarization in ArcGIS. If you're wanting to summarize a continuous variable such as topographic slope or elevation or like mean annual temperature or whatnot, that's generally done with zonal statistics as table. So basically you give the algorithm zones, so that could be zones defined as using a polygon vector layer, or zones as like raster zones, like a categorical raster grid. And then within each of those unique zones, it's gonna calculate statistics from the cell values for the thing you're wanting to summarize. So getting, for example, the min, max, range, mean, standard deviation of elevation measurements within a zone. So basically you'll end up with a table that can be exported out, or you could join it back to the aggregate, the zone units like the polygons or whatnot using a table join. One thing should be noted with zonal stats as table in ArcGIS Pro and Arc Desktop, if your zones overlap, so they spatially overlap, then you actually get incorrect and weird examples. It only really works if there's no overlap, and that's because it has to it converts the polygon vector data into categorical rasters as an intermediate. You can only have one value at each location. Zonal stats as table is not generally used for summarizing categorical data. If you want to summarize categorical data, such as like land cover types or soil types, that's generally going to be done with tabulate area. So that basically is going to give you back the cell count or the land area of each unique code in each zone, right? So these are like land cover codes there. Note that the tool won't give you back percentages, so percent of the zone, as opposed to it just gives you back areas. If you do want to get percentages, you have to just do some table math afterwards. So for example, if we wanted the percent of code 41, you would basically take this value and divide by the sum of all the values. This also has the same problem that zonal stats as table has. So if you have overlapping zones, you're going to get weird output. So they should be non-overlapping features. Again, it's because there's polygon to categorical raster conversion occurring as an intermediate step. Okay, if you're not an ArcGIS user or you want a free option to do these types of analyses, then in QGIS these are some comparable tools. So the sample raster values tool can be used to extract raster values at point locations. Zonal stats does zonal stats, so summarizing a continuous surface like elevation within zones. Zonal histogram is effectively equivalent to tabulate area, so for getting area of categories by zone. Merge can be used is similar to like mosaic to do raster, so merging a bunch of raster grids. It can also be used as stack, so to stack bands or merge spatial extents. It depends on the data. So that can be used for merging and stacking. The clip raster by mask tool is obviously for extracting out a subset using a mask. And then raster masking is another way to do that using Saga within QGIS. So basically all the techniques I just talked about with examples in ArcGIS, you can do the same thing inside of QGIS with comparable tools. Okay, so we're going to stop here for the first video, and the next section we're going to look at using Caret specifically, so just some example syntax and techniques within Caret.